computer. Okay. All right. So, so the overall process was such that basically we wanted to calculate the yield of the cement slurry, and that is basically calculated per cubic feet of slurry that is being produced by mixing a sack of cement, right? And a sack of cement is basically one sack is equal to 94-pound mass, right? So what you do is basically a mass balance, volume balance calculations here. And the first thing that, since we have salt here, right? The first thing that we wanted to calculate was basically to calculate the specific gravity of the salt mixture, right? The brine mixture, basically, right? So we did have the specific gravity of class A cement and also the specific gravity of bentonite. So a specific gravity definition was density of basically that component that you're calculating the specific gravity for divided by density of water. That's the definition, right? So if you have the specific gravity, you know what is the density of water, you can calculate the density of that mixture, right? Having the density, basically density is equal to mass per volume, right? And you can calculate basically the volume from this equation, which is mass over density, right? So you would need to have the mass, you would need to have the density. Density coming from specific gravity, mass, we will calculate it, right? And then you can calculate the volume of each component in your slurry, right? And those components are for this, basically 2000 feet are 16% bentonite. That's weight percentage, right? So directly you can calculate the weight of bentonite, which is 0.16 multiplied by 94 pound, which is basically one sack of cement again. And then you have 5% sodium chloride, right? So 0.05 multiplied by 94, that's what we did, right? 0.05, 94 pound mass, you get 4.7 pound mass. And then we also have the value for water cement ratio, which is 13 gallons per sack. So you're calculating for one sack of cement. That means that we have 13 gallons of water. And that 13 gallons translates into 108 pound mass, right? Because the density of water is 8.34 pound per gallon, right? Since we have the weight of the water, we have the weight of NaCl, we can calculate a weight fraction for basically this mixture. And once we calculate the weight fraction, we refer to the tables. What is this table? This is not the table I want. We go to chapter 3 or chapter 2. Am I in chapter 2? I am, but that's table 2.3 or 4, I guess. One of these, I think. Table numbers. So, yeah. 2.3 NaCl solution, 2.4 CaCl2 solutions, and based on the solution weight percent of basically NaCl, you go here. If the number is exactly there, you can just write the number, or if basically it's 5%, let's say you have to interpolate between these two, right, to get that value. So what is it? It's a specific gravity, right? So you calculate the specific gravity of that solution. So you have the specific gravity of your salt water, bentonite, and cement, right? So you have all these. You can calculate the volume using this equation, right? Mass per density. How do you do that? It's basically cement is 94 pound mass. That's, you have the mass, right? Divided by the density. Density is a specific gravity multiplied by the density of water, which is 62.4. And that's it, right? That's basically the cement volume in cubic feet for if you basically mix it, right? And then bentonite, we have the mass divided by specific gravity water. For salt water, you have to add the mass of water. This is the water mass. This is the mass of NaCl in this case, divided by the specific gravity of, this is for solution. So you have only one specific gravity value here, multiplied by water density. So you get the cubic feet volume of basically salt water. You add them together, it gives you the yield of your slurry, which is 2.334 cubic feet per sec. So what it means that if you want to make such cement and you have one sack of cement only, it will produce 2.334 cubic feet of slurry. That's what it means, right? Now, why do we need yield? Because we need to calculate what volume basically of slurry we would need and how many sacks of cement is required, right? Now, the volume of slurry doesn't depend on this yield because that depends on the geometry of your system, right? You need to fill up this area. So this is a volume, which is basically calculated by the capacity, right? Capacity of annulus, that's from chapter 1, right? So you have the capacity of annulus multiplied by the length, which is 2000 feet, multiplied by excess factor, right? What was excess factor? Anybody? Come on, you guys know. I'm sure at least one of you know the definition of excess factor. Nope. So the excess factor was basically, in this example, it was 1.75, right? That means that you might have some areas in your system that you will lose your cement to, which is basically because there is a porous area or permeable formation there, right? So you might lose your cement to that area. So you have to have more slurry than what you calculate because of that loss, cement loss, right? So in this case, it's basically 75% more you would need from the normal volume that you calculate, and that is 1.75 in this case, right? So we calculated the annular capacity multiplied by the length multiplied by the excess factor. That's how much volume we would need. And then we calculate the number of sacks of the cement, right? So that is how many cubic feet per divided by the yield. So yield is coming here, right? This is the yield you calculated here. And this is the volume of the annulus divided by each other, 901 sacks of cement you would need to fill up that area. Okay, any questions here so far? Nope. All right, so let's continue. Basically, we want to fill up the other section as well, this 500 feet and also that 40 feet. So what we need to do is basically similar process to what we did so far. So for that part, I would basically create another table. And I do have basically the component, right? For the other part, and also I have the volume calculations, which is in cubic feet. So components for the other part, that 500 feet is given to me. That's Class A cement mixed with 2% calcium chloride and a water cement ratio of 5.2 gallons per sack, right? So that's that part, right? And we already calculated the CaCl2 specific gravity exactly similar way, right, as the NaCl. So I'm gonna go down, write the components. So we have cement, and we have the Ca Cl2 brine component, so volume, right? So again, how much is the mass of 1 sack of cement? Is 94 pounds divided by the specific gravity of the cement, class A 3.14, multiplied by the density of the water, which is 62.4, and that is equal to 0.4, again, 797. So practically, this number will always be the same if you have the same cement, right? The only thing that changes this part of your calculation is the specific gravity of your cement, which depends on what type of cement you might have, right? So that's gonna stay the same, but the other part that would change is basically the CaCl2 brine. So let's go up, see what mass did we calculate for water. We calculated to be 43.4, and we calculated the mass of the CaCl2 to be 1.88 pounds. So kind of mixed together. So you add them to each other. So that's 43.4 plus 1.88 divided by the specific gravity that we calculated, 1.0329 for that mixture, multiplied by the 62.4 again. All right, so if you do that calculation, you get basically the volume. So that's 0.7025. Make sense? All right, so that's it. This is basically the volume. And if you add the volumes, you get the yield, right? So the yield is equal to sum of these two volumes. That's basically 1.182 cubic feet per sack of cement. Okay. So this is the yield of the other cement. The previous one was 2.334. This is 1.182, right? And next is basically to calculate how much slurry volume you would need, right? So V slurry, that is equal to, now again, you need to look at your basically structure of the system to make sure you do it correctly, right? So you have an annulus here, 500 feet, right? With the same capacity as previous part. And then you have this 40 feet in which the volume should be calculated based on the inner diameter of your casing, right? And the length is 40 feet. So we have these two sections, okay? So which we need to add to each other. So if you remember, the annular capacity is 0.6006. 0.6006, and that should be a 500 feet section, right? And then we have a 40 feet section, so pi over 4 multiplied by inner diameter of our casing, which is 12.415 based on the problem. So that's 12.415 squared. This is basically coming in inches squared. So you want to divide this by 144 to make it feet square, because 1 feet square is 144 inches square, and the length of the system is 40 feet, right? So that basically gives you the slurry volume, right? So if you do this calculation, you get 559.2 cubic feet. So that's the total volume, right? That basically needs to be there. So we can calculate also the number of sacks of cement. And that number of sacks is going to be basically your volume, which is 559.2 cubic feet divided by the yield, which is 1.182 cubic feet per sack. And that's gonna give you 473. sacks of cement. So this is that part. So you can calculate basically the total slurry volume for overall process as well. So that's basically total slurry volume is basically this 559.2 cubic feet plus the previous one, which was 2,102 cubic feet. So adding these two, 2,661.2 cubic feet. So that's the total slurry volume that you would need. Not that they are the same thing, they are different type of basically mixtures, right? So, but overall, in terms of class A cement, also you can calculate how many sacks of that cement you would need. So total number of cement sacks is equal to 473, which is for the second part, and 901. And that is basically 1347 sacks. This is the total. This is for that second part, right? And that's it. That's how you do these calculations for basically mass balance. And now your mixture might be even more complex, have some other components in it with different, specific weights. So it doesn't matter really, right? As far as you know how to do this basically analysis, how to put these components together and how to calculate basically the volume and calculate the yield, it doesn't matter how many components you have, right? All you need to know is the specific gravity of each component, and that's it. And also do a correct calculation in this area, right? Understand the problem of how much cement you would need on what area, basically, right? So did I multiply by 1.75 here? I did not, right? So I should basically multiply that number also by 1.75, but this 1.75 I did in my calculations before the class. So there is a 1.75 here for that for that one, and that gives you the same number, but I forgot to put it here. So why I'm not putting it here? Because that area is basically will not be lost. The area that you will lose is basically in the annulus, which is in direct contact with your formation. Okay, so this area, this part, this 40 feet is not in direct contact with the formation, so there is not any loss here. So you would not basically multiply your excess factor to this 40 feet. You just multiply to that 500 feet annulus part. Okay, so this is not in contact with the formation. No excess factor for here, but excess factor for here and here. Okay. All right. Any questions?
No.
Everyone okay then? So this is kind of problem that you would expect in your final exam. And final exam basically, it will cover I mentioned fracture, but I think I should add the pore pressure as well, because pore pressure fracture comes together basically. And it's not hard, right? It's just, understanding of that Benetton's equation. So your final exam will cover pore pressure, fracture pressure, and cementing. These are basically the three areas that will be in your final exam. In tomorrow's exam, however, it's comprehensive, right? Coming from the beginning all the way to the end of fracture. gradient calculations, right? So, yep. Any questions about the exam or